Okay, good afternoon, everyone. So this project, even though there are only 3 of us now at the stage, has been done by 15 persons, 11 students and 4 mentors and 1 academic supervisor. Speaking of which, my name is Mikhail. I'm an associate professor of programming languages at the University of Bergen in Norway. I'm also a co-convener of the ECMA International Technical Committee 39th Task Group 5, Experiments in Programming Language Standardization. And I'm also a member of the ECMA International's Executive Committee. And in this project, I was an academic supervisor. So the question that we asked ourselves and the message that we want to deliver today is this one: how can we enable more contributions from newcomers to web engines? And me coming from university, I had this idea that, we have a lot of people who are eager to learn, and those people are called students. And at the same time, very few of them, probably none of them, actually have some prior experience in contributing to open source projects, not even to mention large open source projects like web engines. So the question was, can we really pull this through? Can we really have students to contribute to larger engines? So let me talk about the setting of this project. So besides ordinary classes, we have these specialized classes which are tailored for students who are taking them. It's usually 5 to 7 students. And the students take those classes not just to get the grade points, but to really get the skills. And as you can guess from the fact that we are presenting here today, this was a successful story. So what's in it for us at the university? So first of all, we care about students making some real world impact. We want them to learn new skills. We want them to have new technical knowledge. We want them to be involved in open source and also in the standardization work. University of Bergen is an active member in programming language standardizations. We also have some members of our research group who contributed to Fortran, to C++, and now also to JavaScript. So for us, it's natural that we want to participate in this. So we want to bridge academia and industry. Just another successful story that, okay, this is actually possible. We can collaborate. And what's in it for the browser vendors or the web engines? So using students can help accelerate prototyping or implementation of simple features, but actually, as it turned out, not only the simple ones, but also more sophisticated ones. And we naturally, at the universities, care about education, so we could, based on our own learning experience, prepare tutorials and educational materials for others. So how did we structure our project? So we looked into 2 proposals by TC39, Upsert and Temporal, and we ran 3 case studies. The first case study was to implement the Upsert proposal in SpiderMonkey with a support from a mentor from Mozilla. The second case study, we thought, okay, can we, based on the experience in the implementation in SpiderMonkey with a mentor support, implement this in V8 without a mentor support? And then the third case study was, can we explore something a little bit different? We wanted to indirectly contribute to V8 by contributing to a smaller browser engine, Boa, with mentors support. And our talk today is the presentation of these 3 case studies. And I am giving the floor to Jonas.
Hello, can you hear me? Great. I will be talking a bit about implementing the Upsert proposal, first in SpiderMonkey and then in V8. Quick about me again. I'm a master's student at the University of Bergen, currently specializing in algorithms and programming theory. And I'm probably the newest delegate of TC39. And also for the first case study, I had some other students with me implementing this and also writing a tutorial on the implementations. So quickly, what is upsert, or the newer name, the get or insert? Very simply, given a key and a value, check if the map contains the key. If it does, return that associated value. If not, insert new key pair, and then return a new value. Very quickly. And this is a specification text for it. As probably many of you know, the specification text mainly says what the proposal should do, like define the behavior, and not necessarily tell you how to do it, but in a very abstract way say what it should do. So this is like what we're trying to follow in the start, and then we build on top of this later. So we started out with implementing it in SpiderMonkey, and SpiderMonkey actually gives you a version of JavaScript which they call self-hosted, and it's a very easy way to start with an implementation, and actually gives you a quite performant implementation also. It's very similar to ordinary JavaScript, plus minus some features. And it's very easy to learn on the go by just looking at other implementations and taking like certain ideas from them and adapting them to our solution. So now that we know like a little bit about the background, let's go take a quick walk through the good, the bad, and maybe not so much the ugly, because it wasn't that much of it. So the first thing we did when we actually wanted to implement it, we actually had to start by navigating the code base, or figuring out how do we find what we want. We quickly figured out we have helpful tools such as SearchFox for SpiderMonkey, which makes the finding of prior implementations very easy. And then we figure out which folders and files we actually want to work in here. We can simply copy another's function declaration and then just rename it and tweak it to our needs. And these first steps you see here is just some boilerplate code that is very easy to just tweak to our solution, so we didn't really need that much help here. But on to the next step. Now that we actually have a function, it doesn't do anything, but we want to tell the engine about it, which means that we actually have to hook it in. And this is where it starts to get a bit more complicated. The hooking in itself isn't that bad, actually, but knowing where to, which files to look into and what sort of thing you should write is not very intuitive, as a new beginner. So here we actually needed some of our mentor support to figure it out and just point us in the right direction. And then we quickly figure out what the different arguments that we use here are. The next thing we went on to is just, again, looking at other implementations. We based much of our implementations on a map.groupby functionality, as it's very similar in how it works and what it should do. And by copying it and just tweaking a bit, we actually got a specification accurate implementation. But as most people know, we don't necessarily want a fully spec accurate implementation. We want a performance one. So as long as we match the observable behavior, we are allowed to tweak the implementation to make it more performant. And the main place for this is, of course, this for loop that iterates over all entries in the map. And we, of course, don't want it that slow. So then we started looking into, can we use some of the already implemented functionality for the map class, such as this map.has. Here it's std_map_has, which is just a self-hosted name for this function. And it is pretty straightforward to use this functionality, and you can call C++ code as it has been defined in, except that it was not exposed to the self-hosted code. It is easy to make it exposed. You just move the variable declaration in an H file from private to public. But so even though we figured this out ourselves, we still expose more functionality to self-hosted code, which we weren't sure was something we could do and go ahead. So we just had to like have an OK from a mentor, like, yeah, this is something this is fine to do, and it's secure and it's safe. We also implemented another version of this proposal, the map getter insert computed, which instead of a value takes a callback function. That is, if the key doesn't exist, it evaluates the callback function and then inserts a key pair based on this evaluated function. And for performance reasons, we tried to rewrite both of these in C++. But actually, during our review, when we actually wanted to get it into SpiderMonkey, we got a comment that asked about performance on the getter insert computed version, as calling JS to JS code in C++ is actually often slower than just calling from the self-hosted, which means that we would then have to do some performance testing, and as it turned out, leaving getter insert computed as a self-hosted version was actually faster than rewriting in C++. So we decided to keep getter insert as C++ and getter insert computed as self-hosted. The actual rewrite to C++ was surprisingly easily, actually. It's a bit more boilerplate code that's also outside of this function, but most of the functionality is here, and it's sort of you just, again, look at our implementations and then just adapt them. And it's actually pretty straightforward. Most of the work is hidden in some functions called get or add, which was already defined. But during a refactoring of the map class done by Mozilla, like in between our implementations and our actually wanting to push it into Firefox, it got removed, so we had to then re-implement it and tweak it a bit, and also the rest of our C++ code, of course. So it was like some more work, but the refactoring was quite easy. Another thing we didn't know until the actual code review was that we had to reserve these function names in the common property file, which is just another way for the parser to make more efficient use of these names, as they're like something it should look for. And after doing all this, we actually have a working implementation that you can find in Firefox nightly. Of course, we had to do some extra like nightly stuff, adding some nightly guards, which we also needed some support from our mentor to just have some examples of what we should do, but also quite easy, actually. Now, let's take a look over on V8, which we did, of course, without a mentor. And V8, in the same way as SpiderMonkey does, gives you a language to try and make it easier to implement built-ins, specifically Torque, which is just a domain-specific language for V8. It's a high-level abstraction to, again, write built-ins functions. It has TypeScript-like syntax. A lot of built-ins are now defined in it, and we can model our solution by it. The V8 team actually gives us a starting guide and a user manual for Torque, which was very nice and helpful. And there also exists a VS Code extension to give you syntax highlighting and error messages instead of you having to try and compile it every time. So with all these extra things, was it easier to implement this functionality in V8 compared to SpiderMonkey? Not really, for some other reasons. A bit more about the Torque that becomes relevant later. Torque is actually transpiled to something V8 calls CSA, or Code Stub Assembler, which again is a sort of domain-specific language, which is also a mix with C++. Here you see from just the Torque user guide, just how it all works. It takes the types and splits them up and generates some CSA code from this, and eventually compiles it further. So, as in SpiderMonkey, we wanted to base our implementations on other previous work done on the map class. So we started out just looking and For now, all that's been implemented for the map classes are actually just this map.groupby. But as opposed to SpiderMonkey, the implementation was not really that similar enough, and they had done some other work with it, which made it too difficult to actually use it as inspiration. So after looking around for a while and then thinking about like the data types, we figured out that the set class uses the same data class behind. And we can just look at some functionality for this, like set union and set difference. And by looking at all this, we are actually able to do the first couple of steps of the specification quite easily. Another side note about torque again. It's trying to do do a lot of optimization. So it will complain if you have unused variables, at least if you don't prefix them with an underscore, which took me a while to figure out because the error messages I got when compiling was not very helpful, or they were hidden by a lot of other things. But this actually got fixed at some point. We didn't report it, but it got fixed at some point, and the transpiler now actually shows error messages that it will fail your compilation if you don't put an underscore before unused variables. Another thing is that since torque is a transpiled language, if the error shows up after it has been transpiled, it's often quite difficult to actually understand and parse the error messages that's been generated from this code. So let's look at actually the step 4.a, which is just a comparison, which was surprisingly another pain point. Now, torque does do some overloading of the comparison operator, but there is some comments there about since we're not sure about what types we're actually comparing, we cannot use this overloaded function operator. So which means that we have had to figure out which function call to actually do the comparison, which was not very easily found, but we figured it out. The next step is more about how do we call some already defined map functions, such as the map.set if you want to insert keys and values into the map. And there should be some way to call runtime functions such as these. I have not been able to figure it out. I have used probably weeks on it, did not get it to work. So instead we found another solution, which is just declaring the functionality of map.set and just copying over the body. And as it says, without mentor support, it is a bit hard to actually know what should we expose, what should we redeclare, and what should we change to make our solution work. And is there some other way of going around this? Now, I believe this is actually sort of the right solution, as you don't want to do runtime calls in V8, as it's not as performant as just inlining the code anyways. But we have no way to be sure without anyone actually looking over our work. So now that we have figured out how to write functions in CSA and how to expose them, optimizing the solution in the same way as we did in SpiderMonkey was pretty straightforward, since we sort of just did the same again. Lastly, we want to give a special thanks to Daniel Miner, which volunteered as a mentor for the first case studies. And I think I'll leave it over to Shane now to continue.
All right, you can all hear me? Great. I'm here to tell you about case study number 3, which is Temporal in Boa and V8. So a little bit about me. I'm the convener of TC39TG2, that's the Internationalization Task Group in ECMA. I'm chair of the Unicode IC4X Technical Committee. That's my GitHub. But the hat I'm wearing when I come to speak with you today is as a mentor from January to May of this year of this project with the University of Bergen. So first of all, just a little bit of an intro. Hopefully most of the people in this room are a little bit familiar with the temporal proposal, but if you're not, it's the proposal that brings modern date and time types to ECMAScript, and these are the types that it brings into the language. This is a proposal that is consistently rated as one of the top proposals for having demand from developers. So as it turns out, with dates and times, as you might know if you've worked with dates and times before, dates and times are challenging. And they're just as challenging to implement in an engine as they are for you to use in your developer-side code. So I'm just going to give you 10 example reasons why implementing temporal in an engine is challenging. One is that it is a giant specification. In fact, the temporal specification, the temporal proposal, when it's written in EC markup, is longer than the entire ECMA 402 specification for the Intel object. So it's quite a big proposal that needs to be implemented. The Intel proposal took many years to build up to where it is now, and temporal is like, go do it all at once. The second reason is that as being a very large proposal, it's sort of a mini specification in itself, and there's lots of changes that get committed to it, both normative and editorial changes, which creates a bit of a moving target, so that if you're trying to do like a multi-year project, implement temporal, and then the temporal specification is 50% change from what it was 2 years ago, it's a bit of a challenge. The third is that there's, of course, many edge cases. What happens if you add a month to February 29th? Like, I don't really know, but there's written in the specification somewhere. Someone needs to figure out what that means. Many different types of edge cases. You have to integrate with a time zone database. Typically, engines ship a time zone database, and that's different between each engine, and the exact interface that you have there, trying to interoperate with the time zone database from the operating system if you have one. We have to figure out how to do that with temporal. We have to have calendrical calculations. We have to be able to figure out if you're in a Hebrew or a Gregorian or a Chinese calendar, exactly what should we be doing and what's the right thing to do in those cases. After we land the specification in an engine, it is a large code base for the engine to maintain, right? So the bar for landing this code into the engine is a bit high, because it's like, well, you're adding all this code, all these lines of code, like who's going to maintain this code going forward? That's a challenge. Many proposals, like the one you just saw, like one person can probably fit the whole proposal in their head. Like, that is not going to happen with temporal. And like in general, like, you need a team to implement this. It's not possible for just one person to implement it. Don't want to say it's not impossible. I don't want to say that contributors like Anba are not like can't do it. But like, for regular people, like, you're not going to have one person implementing all of temporal. We need to be able to align with the rest of the specification, so there's a lot of testing that needs to happen. Everything needs to be reasonably efficient, and of course, all this needs to be interoperable across engines, right? You have V8, you have SpiderMonkey, you have JSC, you have all the other JavaScript engines that run on different types of embedded devices and everywhere. Like, we all need to agree somehow. So there's a couple different ways that we looked at for how we can implement temporal in an engine. Two of these approaches. One of them is to just land it directly in an engine, right? This is what SpiderMonkey did, where you just land the code in your repository and you're done, right? The other way, which is the way that I'm going to talk about more in this presentation, is what if you can use a third-party library to implement it? So let me talk about using a third-party library. So what does this mean? It means that what if you can take the specification and you can write it in a library, in a standalone library, in a standalone package, just like a package that does one thing, which is implement temporal, and then you can have engines use the library to just add their bindings so that you can use temporal in your engine. There's some advantages for considering this type of route. For example, it has a lower upfront review cost and maintenance cost for the engine, because the engine only has to maintain a thin wrapper layer that does JS bindings. It doesn't have to maintain the rest of the implementation of the specification code underneath it. A second one, which I think is really important, is that it brings a bigger ecosystem to maintain and improve the library over time, because the number of people who can really learn to contribute to an engine directly, like SpiderMonkey or V8, right, have to go through the whole learning process that we just heard Jonas tell us about, right? But if you can implement this in a nice standalone library with a lot of tooling around it, like, you can build up a much larger ecosystem. You might even have non-engines just who want to use temporal, like maybe even use this library in non-web contexts, right? And then some success stories here are Intel is in every engine that I know about implements it using a library. Regular expressions commonly use libraries. JSON and other things also tend to use libraries. So this is not completely new. There are examples of this in the web platform. So I'm going to talk a little bit about this slide now. If you've contributed to Chrome before, you might be a little bit familiar with this diagram. This is the Chromium, what they call the rule of two. The rule of two means that when you write code and contribute code to V8, it can be two of these three things. It can be written in C++ in an unsafe language. It can process user input, and it can run with no sandbox in the browser process, right? And you don't want to do all three at the same time. And Temporal is a library that we want to be able to have, we want to be able to process untrustworthy inputs because it's a user-facing library, and it needs to be part of the core engine. So how do we do this? That's when Rust comes in. According to the Google security blog, this was published over a year ago now. This is a screenshot I took, so these are not my words. This is why they're choosing to bring Rust into Chromium. I don't have to read to you all the details here. The one that matters for us is that it helps us solve the problem of two by being able to implement code in a safe language. So let's go ahead then and talk a little bit about, I'm going to introduce to you some concepts which I'm then going to wrap together in the slide that comes after this one. So let's talk about Boa, and let's talk about Temporal RS. So how many people here have used Boa or heard of Boa before? A few people. Actually, that's like almost half the room. That's great. It's a JavaScript lexer, parser, and interpreter written in Rust, which is quite cool. And Temporal RS is a standalone Rust project that Boa has been using to implement the temporal specification. Temporal RS used to be part of Boa itself, and then we worked closely with the temporal maintainers to pull it off into its own library called Temporal RS. So the state of temporal in Rust gives opportunities for V8. One is that we have a library that is specifically aimed to be compliant with the temporal specification. A lot of people are like, oh, can't you just wrap an existing library Rust Chrono or something like that and implement it in the library? Well, not really, because it doesn't implement the specification. It doesn't have all these edge cases the way that temporal says they should be, right? ECMAScript made certain decisions about how you handle all these edge cases, and those edge cases have to be handled in that interoperable way, right? So the advantage of this particular library is that it aims to actually implement all the things that Temporal needs the way that Temporal wants them to be solved. And it's the only library that we're aware of that does this way. The lead developer of Boa is conveniently a Temporal proposal champion, Jason Williams. It's written in Rust, so it solves the rule of two problem I just explained in the previous slide. And another sort of side benefit is that it gives us an on-ramp to use other libraries like ICU4X. I'm the chair of the ICU4X technical committee. It gives us an on-ramp to be able to use that in other places in the V8 engine. So this is basically what the architecture looks like when we take this library-based approach. You got Temporal RS that depends on various different components. It uses ICU4X to do the calendrical calculations. It uses other libraries to do things like IXDTF string parsing for dates and times. And then we've got the Temporal RS, which is then used in both engines, Boa and V8. So, but again, what am I here to talk to you about? I'm here primarily to tell you about this case study in terms of my cooperation with the University of Bergen. What I did was, over the last several months, we did a project that I mentored a project to bring Temporal RS to spec compliance so that we can use it in V8. So I mentored 6 students that you can see here. In the form of a weekly 1-hour meeting, and I also gave a little Rust mini course at the beginning of the semester so that we can get onboarded and hit the ground running in writing Rust code. The students contribute primarily to the Temporal RS library, as well as there's one student who contributed also to the test 262, and there's one student who contributed to the bindings into Boa. But this was primarily a Temporal RS project. I want to give special thanks to Kevin and Philip. I think at least Philip is in the room here for responding quickly to pull requests and helping us land those and helping us get unblocked. Okay, so this is what the code kind of ends up looking like. So Henrik is one of the students that I mentored. This was a commit that he landed just a couple weeks ago. And the left side, we've got the temporal RS code. So this is just a regular like Rust library. It has a function. The function has like it's statically typed, and it has an API that's very similar to the temporal specification, but in a very more rusty way, right? On the left side, and on the right side we've got like Boa code, right? So this type called plain year month and plain month day, those should be the same. That's a type on the slide. Those should be the same type. But we have this type on the left side. It's like the Rust type. On the right side, it's the like JavaScript wrapper type. And then the code on the right side calls the function that is then living on the left side. This is basically the whole, what you see on the right side is basically the entire Boa code. So basically it takes the object, it checks that it's like a valid JavaScript object. It validates some fields, which I highlighted that part, but it's basically like, is this field in range, right? And then it calls over here in the Rust crate, it calls that one function, and then it basically converts it back into a JavaScript wrapped object that it can return. So the Boa code is very small, and then all the complicated spec logic lives on the left side inside the Rust library. All right, so here's my favorite slide in the presentation. The goal was to take this Rust library, which when we started had not such a great spec coverage, and bring it up to higher spec coverage, so that we can then leverage it. In Q4 2024, this was the Test 362 coverage of the Boa engine. It's about 37%. There's a big gap. By Q1 2025, right before we started the Bergen project, it got to 67%. That's after Kevin landed some time zone calculations into the engine, and then. I think we can take credit for most of this last jump here from 67 to 92%. That was the work that we did with the students at the UIB in order to get this library up to 92% conformance. And just as of like a few weeks ago, we've also now done the second step, which is, okay, what if we take the library and wrap it into V8? And this is code that if you build V8 and run the REPL, you could get code like this running. And this is running using Temporal RS. This is running using Rust code in V8, which like a year ago was like not something anyone was like, is that ever going to happen? Well, this is running like if you clone V8 and build it right now, you can do this. So this is V8 using a Rust library to implement Temporal. My colleague Manish, who's not with us today, has been driving this side of the project. It's possible that we'll work with additional students and other things to sort of help us build up the V8 side of this. Cool. I have just a couple slides left for you. The first is going to be lessons that we've learned from using this approach to implement a big proposal. So first, some successes. Overall, using a library, we were able to reduce the barrier to entry. So we were able to implement almost a dozen different functions. We started with I think the duration total function, and then we implemented a lot of things like a lot of type conversions. When you just saw was like plain year month to plain date. So we implemented a lot of different functions that were stubs, and we filled them in with actual code. And in order to do this, like all we had to do was like use a very a fairly large ecosystem that exists of Rust courses. So like if you want to be able to contribute to a web engine, all you need to do is like learn how to write Rust code, and if you can do that, you can contribute to an engine. You don't have to learn how an engine works, you just have to learn how to write Rust code, right? So this, I think, really did help us reduce the barrier to entry and help us really scale out and have these students be able to be more impactful. Second is that the library is also more amenable to long-term maintenance. For reasons I stated earlier, we now that we have like all these students and a much bigger group of people who can review this code, right? We can also maintain this code moving forward, as opposed to just like a very small number of people who've like onboarded into how do you write V8 JavaScript bindings. And one question I get a lot for why should I use Rust? Why can't I just use C++? We've been using C++ for years. One of the big things for me is that, I'm a very busy person, as I'm sure many of the people in this room are. Like, I don't have time, like when someone sends me a pull request, to be like, does this C++ code have a null pointer exception somewhere? Like, am I going to have a dangling pointer? Like, I don't have the time to figure that out and to think about that. With Rust, like, if they submit a Rust code that's fully safe, like, it's not going to have a dangling pointer, which makes it much easier for me to review the code and be able to scale out to a much bigger ecosystem of contributors. These are some lessons learned and areas we need for more discussion. Things that we should work on. Some maybe drawbacks of this approach. One thing we found was that when our students were implementing these functions, they didn't have a way to test them, because you write the code in Rust and then you want to test it. Like, you can write a unit test, but really what you want to be doing is running the test262 suite, and now you're like one step away removed from that. The way that we resolved this issue was that we had all of the Boa functions implemented as stubs. So we implemented the entire wrapper layer before we implemented the spec text. We had to-do comments inside the temporal RS code, so they were stubs, so that we were able to go and then run the test262 test very easily and quickly. I think that's probably a good approach to be able to solve this kind of problem, but this was one pain point that we experienced. How do you run test262? A second one was, it requires an extra, for students getting onboarded into Rust, it does give a little bit it does require a little bit more onboarding, relative to what you learn in your class. You might learn how to write C++ or Java in your class, but you don't necessarily learn how to use Rust. Hopefully this is changing as more, universities sort of, teach Rust in higher level classes and things like this, but this does, it's a little bit of a barrier to entry. The third is that we found this, especially when we're doing the V8 wrapper, is that handling of slots and option validations works differently. What I mean here is that the temporal specification is like read field, validate in range, read field, validate in range, read field, validate in range, and then go do the rest. But when we're running in temporal RS, we already need to have everything read before we can actually run the spec, which means that we then process options in a different ordering. So this is still a question that we're still working our way through. But that's one thing that I think, this is more a question for spec authors, please write your specs in a way that makes it amenable for putting into a library. And then this is a question that I sometimes get when we're talking about libraries. It's well, libraries are great, but if everyone uses a library, then do you really have multiple implementations? Because part of the point of being on the web platform is you want to be able to have we want to be able to make sure that the specification is actually implementable multiple times. And if you have multiple engines all using the same library, do you really have multiple implementations? So that's kind of an open question. With Intel, everyone basically uses one implementation. We're working on changing that though, but with IC4X. But this is just generally a question and a good, just some food for thought. So I think at this point I get to turn it back to Mikhail to close us out.
Thank you. Yeah, so to conclude, for the Upsert tutorial, for the Upsert proposal, the students were able to implement it in both SpiderMonkey and V8 with and without a mentor. And coming again from an educational institution, we thought that it's sort of our duty to share this learned knowledge with the community. So the students have written themselves a tutorial, pretty detailed one, on how to start contributing to SpiderMonkey and V8 and how to essentially replicate all the steps that they have done in course of the case studies 1 and 2. And for the temporal implementation, we took a different approach, where instead of trying to teach the students on the details of the V8 engine, we took a different approach and leveraged standalone Rust code. Essentially, this greatly lowered the barrier of entry for the students, and we were able to benefit from modularity and reuse of implementations. We will also have a breakout session on Wednesday at 12, where we will discuss more detailed how to involve students and also researchers in web engines implementations. Thank you very much.
Thank you all. Hi. Thank you all. Because we're short on time, let's make the questions quick and fast, if we can.
Okay, since it's supposed to be fast, then I won't sing you Sangerhilsen. Otherwise, I would. But yeah, I guess you kind of already answered this. But as an author of yet another JavaScript engine in Rust, how do I contribute or collaborate with Universiteetti Bergen to work with your students?
Well, you are very welcome to do that. So, as a co-convener of TG5, the TG5 maintains a list of open, issues. The student projects are not necessarily there, but we can still do that. So you're very welcome, and we will be very appreciating your collaboration. So I can just probably talk to you after the session.
Yeah, hello, is this good? Yeah, I want to, first I wanted to say congratulations for the work. This is really great that you're doing here. And I have a question regarding like the initial part that I don't see that you describe it. It's like, how did you pick these tasks, and do you have any other tasks in mind, and did you have any learned lessons about what kind of tasks are interesting in these environments for the students?
Okay, so for the Upsert proposal, so this was in I think in June 2024, so last year, at the TC39 plenary, there was a discussion about the proposals that haven't been, actively worked on, and Upsert wasn't worked on like for 5 years back at the time, and then initially we planned this as just a way for the students to get some experience in implementation of that old state of the proposal, but then it actually kind of turned out that it actually makes sense to revive the proposal. And yeah, so this was kind of not initially planned like that. So you want to talk about the temporal, or?
Yeah, I can talk a little bit about temporal. So, we had this problem we wanted to solve, which is that we have the temporal RS library, which is at 67% compliance. How do we get it to 92%? Like, where do we get the resources to put behind this? Like, I want to find people on my team to be able to contribute to it, and like, we do have people on my team contributing to it. But like, how can we really accelerate this, right? And the Mikhail generously offered, like, do you want to mentor like next semester's pod of students who are doing this project? And I'm like, I think we can make this work. And I think that this is a good example that like we can make this kind of thing work, right? There's a lot of people who are learning how to code, and when those people, they can contribute to like class projects, right? But like they can also contribute to something that has real impact too, right? And while also learning, how to code in the process. So I think it's really a win-win. And like one reason that I thought Temporal RS was a good approach here was that like it is a self-contained project that has very clear that has very clear deliverables. So and it also has many different things that can be divvied out amongst different students. So I thought that it was very appropriate, and it ended up working out.
Yeah, this is all amazing. One kind of through line that I feel like I saw from the talks, the initial half was around optimizing this kind of simple function in the engines, and then the other half was like bringing in a library to do like a whole load of work. And I'm curious, do they run into conflicts? Like the idea of a library gives you this like very broad but unoptimized case, but doing those kind of very detailed optimizations within each of the engines, do you start to lose the value of a library? Or is there like, could you make a claim that like temporal is not as well optimized as it could be because it's leveraging a library? And I'm just wondering if you could talk to that a bit.
Yeah, I can definitely speak to that. So First of all, the examples that I like to show, regular expressions, INTL, and JSON, are largely implemented in libraries. And like regular expressions in JavaScript are like something where we can focus a lot on optimization. And in fact, by using a library, we can actually we can use basically like all of the Rust tooling for like how can you like optimize this code to run very efficiently. So like you can really focus on building a very highly performant a body of code that is in the form of a library. Right, and then the question is really like, well, how can we make sure that the wrapper layer that sits between the engine and the library, like doesn't lose the performance that we've already gained when we've built this high performance, low memory usage library, right? And this is something that's that's I don't have the numbers quite yet for V8 because it's so new. Hopefully, I'll have some numbers soon that we can share and look at. But like, given the experience that we have had with regular expressions and INTL, like I think that this is definitely a solvable problem. And I don't think that writing the code natively in V8 is necessarily going to give you code that is faster than if you can write it in a library. I think this is largely an integration problem more than it is like an actual technical problem. Yeah, I think that's a good question. I need to think a little bit more about that. I guess my initial thought would be that like it makes a lot of sense for a library for it to be sort of a cohesive object, right? So like map upsert is maybe more appropriate as like if you have a map object, maybe you implement the whole map object, right, in a library, and the map upsert can be added to that, right? So I think that's probably where we're like, at least initially, I think it would be appropriate to draw the line. Does that answer your question? Cool, yeah.
Right. Thanks, everyone. Of course, you can find all of our speakers at the breakout room as well as in the hallway around. Thank you for your presentation again. Yep. All right.